Hello, everyone. Welcome to the pre-recorded lecture of our version of our lecture number 4, which will take place in person on Friday, January 21st. So this one might be a little bit shorter than some of the previous recordings, just to keep it in sync with the in-person lectures, which will start from a slightly earlier point. So basically, we're in section 1.2. It's a review of matrix algebra. We've talked about matrix multiplication quite a bit. And I just want to mention 3 more concepts from matrix algebra that are going to be important for us and that we should probably know about from the outset. So they're probably somewhat familiar, but we'll just recall them. Anyway, maybe some of them are not entirely familiar. So the first one is the n by n identity matrix. So we've been talking about matrix multiplication. And basically, for the n by n identity matrix is a square matrix that has a so-called neutral property with respect to matrix multiplication. When we multiply it on the left by a matrix with n columns, we have no effect on that matrix. And when we multiply it on the right by a matrix with n rows, we have no effect on that matrix. So In, what it is it's the n by n matrix whose entries in the 1, 1, 2, 2 positions, which are referred to as the positions on the main diagonal from the upper left down to the lower right, those are all 1, and all the entries in all other positions are 0. And so, for example, there's the 2 by 2 identity matrix and the 4 by 4 identity matrix. And what makes this matrix special is that it has the so-called neutral property or identity property for matrix multiplication. Multiplying another matrix by it has no effect. And what that means is that if A is any matrix with n rows, so A is a matrix that can be multiplied on the left by the n by n identity matrix, if that happens, then you just get A itself back again. And if B is any matrix with n columns, then it can be multiplied on the right by the n by n identity, but that has no effect on it. You get B itself. And then finally, if C is a n by n matrix, so it can be multiplied on both sides by another n by n matrix, such as the n by n identity matrix, then multiplying it by the identity on either side has no effect on it. So just to sort of see why that is, I guess, in our context of matrix multiplication, if we apply it, for instance, to a vector v with length n, so INV would be the n by n identity times the vector whose entries are v1 down to vn. And if we do that calculation, we get v1, the first entry of v, multiplied by the first column vector, the first column of in, which just has a 1 in the first position, 0s everywhere else, plus v2 multiplied by the second column of identity matrix, and so on, down to vn multiplied by the last column of the identity matrix. And when we look at it this way, we can observe that what we're looking at is nothing other than the vector v itself that we started with, because what the vector with coordinates v1 down to vn actually means is literally v1 multiplied by the first standard basis vector plus v2 multiplied by the second one and up to vn multiplied by the last one, and so on. So the columns of the identity matrix are the standard basis vectors in Rn. So that's just to recall what the n by n identity matrix is and what its properties are. Okay, so the second concept that we will recall at this point is that of the inverse of a square matrix. So if we have a square matrix of size n by n and another called A, then another n by n matrix B is called the inverse of A if the matrix products AB and BA, which both are n by n matrices, if they're both equal to the identity matrix IN. So in this case, A and B are referred to as inverses of each other, and their product is the identity element, which has the neutral property with respect to multiplication. So really the relationship between a pair of matrices that are inverses of each other is similar to the relationship between a pair of rational numbers or real numbers that are reciprocals of each other. So for example, if we take the rational numbers 3 over 5 and 5 over 3, their product is 1, which is the identity element for multiplication of rational numbers. And essentially, as we know, that means that, we can sort of reverse the work of multiplying by 5 over 3 if we multiply by 3 over 5, which we would refer to as dividing by 5 over 3. So a couple of remarks about that. The inverse of a matrix A is denoted by this notation A with a superscript of -1 in general, and that I suppose is reminiscent of the notation for numbers, where we know that x to the power minus 1 means 1 over x. So the inverse of a is something that behaves with respect to a, the way that 1 over x behaves with respect to a number x. The distinction, of course, which we need to be careful about, is that the multiplication of matrices is not commutative. So it's not obvious, for example, in advance, that if AB is the n by n identity matrix, then BA also is equal to the n by n identity matrix, although it is always true. It's not something that's obvious. And it does mean that when we're doing manipulations involving matrix inverses that we might use to sort of try to cancel an A or divide by an A, we have to be careful about whether our multiplication happens on the left or on the right. So, so an example here, these two by two matrices are inverses of each other. We can verify that easily by just calculating their products, I guess, in both directions, both orders. If we do it for just one of the orders anyway, we can observe that if we do this product, we get in the top left, we get 3 times 2, which is 6, plus minus 5. In the top right, we get 3 times 1, minus 3. In the lower left, we get minus 10, plus 20 over 2, so minus 10 plus 10. And in the lower right, we get minus 5, plus 12 over 2, so minus 5 plus 6, which is indeed equal to 1. So yeah, we can confirm that we do get the 2 by 2 identity matrix. Okay. Doubtless you know how to calculate inverses of 2 by 2 matrices and 3 by 3s. We're not going to focus on that right now. We're just going to recall the definition of an inverse and note that not every square matrix has an inverse. So certainly the 0 matrix doesn't have an inverse in the same way that the number 0 doesn't have a reciprocal. But another example of a matrix that doesn't have an inverse is this 2 by 2 matrix whose entries are 3, 2, minus 6, minus 4. And we might notice here that the second row in that matrix is a scalar multiple of the first, if we regard them as vectors with 2 entries. And the same is true of the columns. And that is a clue to the fact that it doesn't have an inverse. As you probably know, there is something also called determinant attached to a matrix, which is a number assembled in complicated ways from its entries. And a matrix has an inverse exactly if its determinant is not 0. But another way to say it in the case of 2 by 2s at least, is that a 2 by 2 matrix has an inverse if its rows are not scalar multiples of each other and if its columns are not scalar multiples of each other. And if one of those things happens, the other one always will as well. So we're going to kind of just note for the moment, recollect the concept and the definition of the inverse of a matrix. We will revisit this topic later and look at some of the remarks that I've just made. So certainly, here, the second row of this matrix is minus 2 times the first row. The first column of it is 3 over 2 times the second column. And, both of these things tell us that the matrix will not have an inverse. And we'll revisit that theme a little bit later in the course. Okay, the third thing to recall is the concept of the transpose of a matrix. So there's lots of things you can do with matrices. One of them is transpose them. So the transpose of the m by n matrix A, so this applies to every matrix, whether it's square or rectangular, is defined to be the n by m matrix. So basically, when you take the transpose of a matrix, you swap the numbers of rows and the numbers of columns. If your matrix is m by n, its transpose would be n by m. And the entries of the transpose of A are rearranged from the entries of A in the following way. The entries of the first column of A transpose are the entries of the first row of A. Entries of the second column of A transpose are the entries of the second row of A, and so on. So for example, if this is A is obviously 2 by 3 here. Its transpose will be 3 by 2. It'll have 3 rows and 2 columns. The entries in the first column of A transpose are the 1, minus 2, minus 3 of the first row of A. And the entries in the second column of A transpose are the 2, 0, and 4 of the second row of A. So there are lots of interesting things in matrix algebra that involve the transpose and things you can sort of think about just, to kind of get used to what the meaning of this might be. You can ask yourself questions like, if A represents a linear transformation, so does A transpose. So this matrix A represents a linear transformation from R3 to R2. Its transpose represents a linear transformation from R2 to R3. So is there anything you can say about the link between those? How are transposes relation to each other? What are their sort of, they're assembled from each other via this kind of rearrangement process, but do they have some kind of algebraic connection to each other? So there's lots to say about that, and it's quite interesting, but not obvious at all. Another way to summarize the definition, of course, is that for entries, the entry in the ij position of the transpose of A is the entry in the ji position of A itself. A remark: if A is m by n, then A transpose is n by m. And that means that A transpose, that product, it'll be a m by n by n by m. So it'll be an m by m matrix, a square matrix. And A transpose A would be n by m multiplied by a m by n matrix. So it would be n by n. So the products A transpose and A transpose A are always defined for any matrix A, and they are always square matrices, and their sizes are m by m and n by n respectively. So the one that starts with A has the same number of rows of A, and the one that starts with A transpose and has A transpose first has the number of rows of A transpose, which is the number of columns of A as its number of rows. Okay. Another remark about these two products, A transpose and A transpose A, is that they have the property of being symmetric. So what it means for a matrix to be symmetric is that it's equal to its own transpose, or another way to say it is that if you reflected about the kind of axis consistent of its main diagonal, then you get itself back again. So every entry off the main diagonal is equal to its kind of diagonally opposite entry. The 1,2 entry is equal to the 2,1 entry. And same for all the other entries. The ij entry in general is equal to the ji entry. Okay, and symmetric matrices are interesting for lots of reasons. They have very nice properties. They also arise quite frequently in applications, and there are lots of things that the property of symmetry enables us to do with them, some of which we'll see a bit later. Okay, one remark about transposes is written here in lemon 9 in the slides. So the setup here is that A and B are matrices for which the product AB is defined, and of course we know what that means is that the number of entries in a row of A is equal to the number of entries in a column of B. Then the assertion is that if you want to know about the transpose of the product AB, you might ask, does it depend on A and on B and on their transposes maybe? And the answer to that is that the transpose of the product AB is equal to the product of the transposes of A and B, but in the opposite order, not in the same order. So the transpose of the product AB is equal to B transpose A transpose. So I've just included a proof of this lemma here because I think it's quite a nice kind of example of how to demonstrate something in linear algebra by just by just figuring out what the entries are and how the entries of the transpose of AB, for instance, depend on the entries of A and B. So it's a little bit picky. It takes a little bit of care to construct demonstrations like this and to read them as well. So give yourself a chance, and don't try to do it too quickly. So we want to prove this lemma, and so that means we need to look at an entry of the transpose of AB, the product, and satisfy ourselves that it's the same as the entry in the corresponding position of the product B transpose A transpose. So since AB, that product, is defined, we can say that A is an n by p matrix and B is a p by n matrix. That's only saying that p, the dimension p, is common to both. It's the number of columns of A and the number of rows of B. Apart from that, the number of rows of A is m and the number of columns of B is n, and we're not assuming that m and n are the same, although they might happen to be the same. Okay, so if we choose a position ij and look at the entry in the ij position of the transpose of AB, we want to show that that's the same as the entry in the ij position of the product B transpose A transpose, which we know is the scalar product of row I of B transpose with column J of A transpose. So let's see. Well, the position in the the entry in the ij position of AB transpose is the entry in the ji position of the product AB itself. Okay, and that's the definition of transpose. The entry in the ij position of AB transpose is the entry in the ji position of AB. And we know what that is. It's the scalar product of row J of A with column I of B. Okay, so we can write it this way. It's the sum over all the entries in row J of A, which go AJ1, AJ2, and so on, each multiplied by the corresponding entry of column I of B, which is A1, or B1i, B2i, and so on. Okay, but the entry A, so this sort of relates the ij entry of AB transpose to entries of A and entries of B. So we kind of want to express the entries of AB transpose in terms of the entries of B transpose and A transpose. So we have to kind of rearrange the right-hand side here so that it refers to entries of A and B transpose rather than A and B themselves. So we can certainly observe that AJK is AKJ transpose, which is written in here, and that BKI is BIK transpose. So what we're saying here is that this entry, after we've just sort of rewritten it a couple of times and redescribed how it's written, this is the sum over K of the entries of rho I of B transpose multiplied in order by the entries of column J of A transpose, and all of those things added up. So K here runs from 1 to P, which is the number of entries in a row of B transpose, or in a column of A transpose. So this is nothing but B transpose A transpose, the entry in the ij position there, which is the scalar product of rho I of B transpose with column J of A transpose. Okay, so the transpose operation has this kind of interesting property that if you apply it to the product of two matrices, you get the product of the transposes of the two matrices, but in the opposite order, which actually makes sense when you think about it, because the product A transpose B transpose need not even exist. Just because AB exists doesn't mean that BA does. Okay, so that's just a few recollections about transposes and identity matrix and inverses. So these things, we're not really going to urgently need them. They're just sort of part of our review of matrix algebra. So we have these words and these ideas in our kind of armory as we go forward through the course and in our vocabulary as well. Okay, that is the end of section 1.2, which is our review of matrix algebra. And what we'll do next is to make a start on section 1.3, which probably is kind of sort of new content for some people. At least the methods in it might be somewhat new, although the problem that we're going to study is one that you have certainly looked at before. So section 1.3 is called Systems of Linear Equations. And what we're going to do here is develop the so-called Gauss-Jordan method for solving systems of linear equations, which has been around for several hundred years, but still is really the kind of cornerstone of most modern algorithmic methods for solving systems of linear equations. So a system of linear equations is what is often referred to as simultaneous equations in the post-primary school syllabus, and we'll kind of develop a systematic method for solving them rather than relying on kind of ad hoc methods for particular examples. So just to remind ourselves, what are we talking about? Here's an equation, 2x plus y equals 3. So everybody is very used to dealing with equations like that. It's a linear equation in the variables x and y. Okay. And one remark about that equation is, as it stands, it's just a statement. 2x plus y equals 3 is an assembly of symbols. It's kind of a formal statement. And it's neither true nor untrue. It's just an expression that has some symbols in it, an equal symbol and some variables called x and y, and coefficients which are 2, 1, and 3 on the right-hand side. So that statement is not true or false. It doesn't have the capacity to be either true or false. It's just a statement involving these abstract symbols. But if you replace x and y with your favorite choice of a pair of numbers, a pair of real numbers, then the statement will become either true or false. So for example, if I put x and y both equal to 2, I'll get 2x plus y equal to 6, which is not 3. So the statement will be false in that case. But if I put x and y both equal to 1, then I get 2 times 1 plus 1, which is equal to 3. So in that case, the statement will be true. So for example, it's true if, for example, x equals 1 and y equals 1. And it's false, for example, if x equals 2, and let's say y equals 1, because in that case, we'll get 2 times 2 plus 1, which is not 3. Okay, so this is nothing that's new, but I guess it's kind of worth having a clear statement of what we mean to say that something is a solution of an equation. So a pair, x0 and y0, of specific fixed real numbers is a solution to that equation if replacing x with x0 and y with y0 in the equation, x0 and y0 now being fixed numbers, if that replacement makes the equation into a true statement. And the set of all solutions is called a solution set. And so, for example, for this particular example, 1, 1 is a solution. It's certainly not the only solution. And as you know, for every value of y, there is a corresponding value of x for which the pair composed of that x and y is a solution, and the set of all solutions forms a line in the plane. So if we plot the coordinates of all the solutions to this equation, we know that they form a line in the plane, which one could, of course, easily draw a picture of if you wanted to. Okay, that's a recap of what a linear equation is, and two variables at least, and what a solution to a linear equation is. Okay, so a linear system is a collection of linear equations in the same variables. So in this example, our variables are x and y. So a collection of such equations is referred to as a linear system, or a system of linear equations. And the solution set of a system of equations is the subset of Rn, consisting of those elements. So an element of Rn is a list of n real numbers, an ordered list of n real numbers, which we can plug in for x and y. And we say that such a point is a solution of the system of equations if it's a solution of each equation in the system, so that when we put in those values of x and y, that all the equations in the system become true. So here's an example of a pair of equations with two variables, x and y, just two equations as well. So, I mean, I know that you all know how to solve these things, but let's just note that we can do it using a kind of ad hoc approach. So the first thing you might do, if you see this system of equations and you're asked to find the solution. So remember what you're doing when you solve a system of linear equations is you're finding the simultaneous solutions of all equations. So I know the terminology simultaneous equations is used quite often, but I must say that I really kind of dislike that terminology, because it's not the equations that are simultaneous. The equations are just equations, and they're two independent equations. A pair of numbers, x, a pair of numbers like x equals 1, y equals 5 or whatever, might or might not be a solution of either one of these equations. But if it's a solution of both of them, then it's a simultaneous solution of both of them. So what we're looking for are simultaneous solutions of all the equations in the system. So I guess what I'm complaining about with the terminology is we're looking for simultaneous solutions. It's the solutions that are simultaneous, not the equations in any way. Okay, in any case, let's solve the system. So if we take equation A and multiply it by 2, okay, so then we get the equation 4x plus 2y equals 6. Okay, which is not the same equation as equation A, like it has different coefficients, but it has the same system of solutions as equation A, because if 2x plus y equals 3 for some pair of numbers x and y, then 4x plus 2y equals 6 and vice versa. So equation A, so this equation, let's call it A dash, is equivalent to equation A in the sense that they have the same solutions. And let's write down equation B as well, 4x plus 3y equals 4. And then what we might do is we might observe that if we have a pair of numbers x and y that satisfy both of those equations, then they must also have the property that when we subtract one of these equations from the other, this pair should still be a solution of that equation. So this is B. So if we take equation B minus equation A dash, we get 0x plus 3y minus 2y is y. 4 minus 6 is minus 2. So we're saying that any simultaneous equation, sorry, I have something to say to myself, any simultaneous solution of these two equations must have the property that y equals minus 2. Okay, and once we know what y is, we can find the unique value of x that, along with that value of y, satisfies both equations. Okay, but I guess the third comment as well is that this new equation is a sort of it's obtained from the original A and B by adding those equations together and by multiplying them by scalars and all that. So y equals minus 2 is not equivalent to either of the two equations that we started with, but we're saying that any simultaneous solution of those two equations must also satisfy this one, y equals minus 2, and then the corresponding value of x, well, 2x is 3 minus y, I guess. So if 2x is 3 minus y, then 2x is 3 minus minus 2, x equals 5 over 2. So hopefully that those values of x and y satisfy both equations. So if y is minus 2 and x is 5 over 2, then 2x plus y is 5 minus 2, so it's 3. And 4x plus 3y is 10 minus 6, so it is indeed equal to 4. So we can be confident that that is a solution of that system. And indeed, it is a unique solution because we didn't do anything that could have eliminated any other solutions. So this is what I'm describing as an ad hoc approach. It's kind of you look at the system of equations, you sort of identify something that you can do that will cause a variable to drop out and that will leave you with an equation with only one variable in it. You do that, you solve for that variable that remains, you plug everything back in, and you get the solution for all the variables. So it's fine, nothing wrong with it. It is an ad hoc approach, but it works, and it certainly works for any system like this, which has just two variables and two equations in it. But if you have a system with more equations and more variables, that might be a bit trickier. And in that case, you might want something a bit more systematic in terms of an approach. You might not want to just kind of stare at the equations and sort of decide what to do from one step to the next on that basis. You might like to have something a bit more definitive, I guess, in terms of how you go about it. So that brings us to the topic of elementary row operations and the idea of using matrices to solve systems of linear equations, not necessarily by representing them in matrix algebra, but by keeping track of the coefficients. So let me briefly introduce this next example, which we won't solve now. That will be our content for the next lecture next Wednesday in week 3, but we'll glance at it at least. So here's a system of equations with 3 equations and 3 variables, still not terribly complicated. So like, I'm not claiming that we couldn't do this using the methods that we used for the previous example. But let's think about the kind of things that we can do when we solve a system of equations and think about how we might sort of systematize those ideas. And then we're going to systematize them into something called elementary row operations, which will apply to a matrix, not to a system of equations. So things we can do, we can multiply an equation by a non-zero constant, and the sort of obvious reason to do that would be in the hope of eliminating some variable after adding another equation to it or something. So for example, here we might like multiply equation 3 by 3 and then add it to equation 2 to get rid of the x, something like that. That's the kind of, we can do that sort of thing. So that we can do that. Second thing we can do, we can add one equation to another, for example, in the hope of cancelling some variable when you do this addition. And I suppose, again, here, you know, we should think kind of carefully about why these operations are sort of permissible. And, you know, if you add one equation to another, you are certainly changing your equations. You know, the new one is not the same equation as any of the previous ones. But the point is that simultaneous solutions of all of them must survive this process of adding one equation to another. If you have a choice of numbers x, y, and z that satisfy all 3 of those equations, then they also have to satisfy any equation that you can get by adding those together or by multiplying them by constants. Okay, so what we're going to do is exactly what I said, like systematize this approach. So what we do is we encode the system of equations differently using the so-called augmented matrix. So here is our system of equations again, and here's a matrix. Okay, so our 3 variables, actually, you know, I'm not going to outline it like that because I want to write something around it. Our 3 variables are x, y, and z. We have 3 equations as well. And from the system of equations, we are sort of creating this 3 by 4 matrix. 3 is the number of equations in our system. 4 is the number of variables plus the right-hand side. So basically, if we look at the entries of this matrix and compare them and look at the system of equations, what we're basically doing is, in each of the first 3 columns, we are writing down the coefficient of x in column 1, the coefficient of y in column 2, the coefficient of z in column 3, and the number on the right-hand side of our equation in column 4. And our 3 rows correspond to equation 1, equation 2, and equation 3. So basically, the matrix here, the 12 entries of the matrix in 3 rows of 4, they kind of encode all the information from the system of equations. Okay, so we have 3 variables called x, y, and z. You know, so if you kind of know that in the background, then you can reconstruct the equations from this matrix. So that matrix is referred to as the augmented matrix of the system. The reason why it's called the augmented matrix is that if you took just the first 3 columns of it, that thing would be called the coefficient matrix of the system. So it's the augmented matrix, it's the coefficient matrix augmented with an extra column consisting of the right-hand side. Okay, so what we're going to do is we're going to work with the augmented matrix instead of working directly with the equations. And we're going to figure out the operations that we're allowed to carry out in the equations, like multiplying an equation by a constant, adding one equation to another equation. We're going to consider those instead in terms of the rows of the augmented matrix. So we'll allow ourselves to multiply a row of the augmented matrix by a non-zero constant. That means multiplying all the entries in that row by the constant. Okay, so the constant could be 2 or whatever. If we multiply row 1 by 2 here, we get 2, 4, minus 2, 10, instead of what's already there. And that corresponds to the exercise of multiplying an equation on both sides by a certain constant, which does change the coefficients, but it doesn't change the solutions. And that's the key point. We can add a multiple of one row to another row. And that corresponds to adding a multiple of one equation to another equation. and replacing that second one with the new thing. Okay, so that again corresponds to an operation which does change the equations, but which doesn't change their simultaneous solutions. So if you have a simultaneous solution of two equations, it's also a solution to any equation that you could get by multiplying one of them by a constant and adding it to the other one. Okay, and the third thing that we're allowed to do, which can be useful occasionally, just because of our scheme that we're going to develop, is we can swap the order of two rows in the matrix. And if you do that, of course, you must swap the whole rows all the way along. And that just corresponds to rewriting the equations in the system in a different order. So it certainly doesn't change the solutions, but it can be a useful thing to do. So these operations are called elementary row operations, or really abbreviated as EROs on a matrix. That they have a really important function, a really important role in linear algebra. They also have an interpretation in terms of matrix multiplication that we have been talking about. And there are, so basically sort of decided on a good sequence of elementary row operations to apply to an augmented matrix is the kind of most well-established means of solving systems of linear equations. And the algorithm for doing it is called Gauss-Jordan elimination. And that is what we will develop in our lectures next week. So that's it for today. If you come along to next week's lectures with a kind of idea of what an augmented matrix is and what these elementary row operations are, you'll be in very good shape for joining along with next week's lectures. So thank you very much, everybody, and we will see you next week.